Okay, so what we're going to look at today, and I'm going to throw a couple of other things in it along with just the truss analysis. We're going to look at a floor truss, a parallel chord flat truss. And we're going to look at, I haven't put in a web pattern yet, and I haven't given you any of the forces yet, because we're going to look at how we're going to figure that out. So I'm going to throw the web pattern in just like this. Almost always this web on the heel panel will come down to the lower corner at the bearing or the reaction. For this one, since there's an odd number of panels, the middle one just can go a random direction. We're going to assume that each of these uprights is evenly spaced. So this is, go a little bit bigger here for just a minute. This is a 20-foot truss. So each of those panels is going to be 4 feet, or 48 inches. So one of the first things we have to do is we have to figure out what the load is, what the force is at each of the joints, because we're going to be looking at the joints. Then we have to figure out what each of our angles are. This angle here is going to be the same angle pretty much everywhere in the truss. So let's go ahead and do that first. Good way to warm up, just reviewing some trig. So what we're looking at is this angle here. This is a 4-foot or 48-inch panel. The truss is 22 inches high, so this is 22 inches here. So this angle, let's see if I go to the right spot. That angle here is going to be the inverse tangent of, what two numbers do I put in there?
22 over 48.
Perfect, 22 over 48, opposite over adjacent. So we'll do that second tangent, 22 divided by 48. And gives us a 24.62 degree angle right here. We're just going to go 24.6 degrees. So that's going to be that angle prevailing pretty much everywhere throughout this truss, at every angled web. Next, I want to figure out what the force is at each joint here, what that added force, that vector is. I have up here 45, 10, 15, loading, 2-foot spacing. What 45, 10, 15 means the first two numbers, as we had mentioned last week, are the top chord loading. The 45 is the top chord live load. The 10 is the top chord dead load. So that 10 is for the floor, the carpeting, whatever else is going to sit on there. Sometimes they'll do a 45-15 if you're going to have like tile floors and some heavy furniture and stuff like that. We're just going with a simple 45-10. Now this is per square foot. Now you'll notice I said 2-foot on-center spacing. Oops, shouldn't say per square. So every linear foot of this truss, since it's 2 feet spacing, if I'm looking at it from above, come on. If I'm looking at this from above, since it's 2-foot spacing, each linear foot of that truss, oh darn it, keep hitting the wrong one. Like here's one linear foot of the truss, contains 2 square feet because it's 2 feet between trusses. So it has 1 foot on each side of that truss that's supported. So that is 45 plus 10 is 55 pounds per square foot, which is going to turn into, multiply that by 2 because each linear foot of the truss supports 2 square feet. That's 110 pounds per linear foot. So every linear foot of the top chord of this truss supports 110 pounds. So now if we go back up here, each of these is 4 feet. We're assuming that they are, symmetrical and evenly loaded. So 4 feet times 110 is 440. So each end of this is 220 pounds. Now right here we get 220 pounds from this side and 220 pounds from this side, so that'll be 440 pounds there. 440 pounds here. 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 And then this one's back just 220. Now I'm going to pause for a second. Any questions on where the 440 and the 220s come from? Sure. So what I did was the top chord, I'm looking at the top chord here, is a 45-pound live load and 10-pound dead load per square foot. So that is 55 pounds per square foot. So if I'm looking at a single linear foot of my truss here, it's supporting 55 pounds. Because it's a 2-foot spacing, there's a 1 square foot on each side of it that is supporting 55 pounds. So each linear foot of that truss here is supporting 110 pounds. So then up above there, I looked at each panel being 4 feet. That's 4 times 110 pounds was 440 pounds, which results in half of that, since we're assuming this is symmetrical, half goes to each end, 220 pounds here and 220 pounds there. However, since this is continuous, this 4-foot panel also supports 440 pounds. Oops, get back here. Half is going to be split 220 to each end as well. So right here we have a combination of 220 and 220. That's where the 440 came from right here. So each of these, the 440 is the fact that it gets 220 from each side. Then this is only 220 because there's nothing on the other side. It's only supporting one side. Any questions on that? Now we have to do a similar thing for the bottom chord. The bottom chord is a 15-pound dead load, so that's for your mechanicals, wiring, plumbing, ductwork, all that stuff. And that is also 15 pounds per square foot. So on the bottom chord, there's also 15 pounds per square foot, and supports 2 square feet. So that means it's a total of 30 pounds per linear foot on the bottom chord. So same type of thing as we did down here. On the bottom chord, 30 pounds times 4 feet is 120 pounds. Total, half goes to each side. So half goes here, so there's 60 pounds here. And 60 pounds here. But again, there's 120 pounds here that's split. So that means there's 60 pounds coming from that side as well. 60 pounds here. So what that means is back here, each of these joints, there's 60 pounds coming right here. This one's got 120 because 60 from each side. 120. 120. 120 and 60. So then our next step is to figure out the reactions. If we look at each of these, it is symmetrical, so we're just going to add up our total load and divide it by 2. Have you guys gone through how you calculate a reaction if they're not symmetrically loaded? Using sum of moments? Okay, that's something we'll look at. If we don't get time today, we'll make sure we look at that on Wednesday. But we have 220, 440, 440, 440, so I'm going to do this here quick. Shrink this up. So I've got 440 times 1, 2, 3, 4, 220 times 2. That gives me a total of 2,200 pounds. And on the bottom I have 120 times 4 and 60 times 2. Which gives me a total of 600 pounds. So I have a total of 2,800 pounds here of downward load. So that means each reaction has to be half of that pointing upward. So each reaction here is going to be 1,400 pounds. Okay, when we go to analyze these, it can be a little bit strange. We're going to start out analyzing this top joint right here. Normally, we would analyze first the heel joint at the reaction, but on these, that top joint is the simplest because there's only one force and there's only horizontal and vertical members coming in. So I'm going to call that joint A. And what I'll do is I'll call this one down here B and this one C for now. This one will be D. So we're going to analyze joint A. So at joint A, we've got truss members coming in from C and B, and we have a 220-pound load going down. And at this point, that is the only force we have is that 220-pound load. If this were a real floor truss, by the way, we would have an additional wall load that we would put there, but I didn't want to overcomplicate it. So anyway, if we're looking at the sum of our vertical forces, we have the 220 going down, that's negative 220 pounds. C is totally horizontal, so it cannot have any vertical component. B is totally vertical, so it can only have a vertical component. So B has to be going completely upright. So looking at this, when I solve for B, B has to be 2,200 pounds. Now from last week, I drew this arrow towards the joint because it has to be going up to counteract the 220 pounds going down. So if that arrow is going towards the joint, is this in tension or compression? Compression, exactly. So that is in compression. Member B is in compression. Member C here, so that'd actually be force B to A, but I did poor notation there, didn't I? That should be force B to A. Is in 220 pounds of compression. Now C to A here is kind of a funny situation. It cannot be in tension or compression because there are no other horizontal components there to work against it. The only way it would have any sort of load on it is if there were a wind load or something like that coming in from the side. We don't have anything like that right now. So the compression or tension on member C is 0. Now it does have loads. It's got the vertical loads that are split. That's where the 220 came from. But we're not worrying about those right now. Those are bending loads. So if I come back up here, this is 0 pounds. This is 220 pounds of compression. So if I go to analyze joint B, on joint B, I have the 220 pounds of compression, and so 220 pounds going down, pushing into the joint. I also have the 60-pound load going into the joint. I have this web here coming from C, and I have this heel panel here coming from D. And then, of course, we have the reaction coming up of 1,400 pounds. So I'm going to look at my vertical forces here. I have a negative 220 because that's pushing down. I have a negative 60 because that's pushing down. I have a positive 1440 because that's pushing up. Right now that would put me at a positive. So I'm going to guess that C here is in compression. What that does is gives me components that look like this. So then I'm going to have a negative CBY, CB vertical force. CBY is right here, and it is going to equal the cosine of that angle, which we said was what, 20? So I'm going to write it down up there. 24.6. I'm going to write it in here so I don't lose it. 24.6 degrees. Times the full force of CB. And this down here is CBX, which is going to be the sine. Oops, I did that backwards, didn't I? Sorry about that. The angle is down here, so this one would be the sine. This one would be the cosine. That's 24.6 degrees times CB. Okay, I'm going to pause there for a second. Anybody need to erase and fix their notes because I screwed that up? So that vertical component, CBY, sine of 24.6 0.416 CB. So that's going to go here. Is that all equals 0? So 0 equals, I've got negative 20, negative 200, negative 60 is negative 260, plus 440 is a positive, was that 1180? Should that be just 1400? Yeah, you're right. Should be just 1400. Is it 220? You're right. Wow. It's going to be one of those mornings, I'm thinking. So 220. Does that all look right now? 220, 60. Yeah. Okay. I'll pause for you guys to fix that. So negative 220, negative 60 is negative 280. Does 1120 work out right? Minus CBY. But for CBY, I'm going to put in 0.416 CB. And now I don't even need a system of equations. There's only one variable there. So let's go ahead and solve that for CB. I'll subtract the 1120. So So negative 1120 equals negative 0.416 CB, and divide by 0.416, negative 0.416. So right in the CB is 2,692 pounds. It's in compression. However, we still need to find dB here. So to find dB, we're going to be looking at the sum of the vertical forces, or sum of the horizontal forces. So right now, the only horizontal force we have other than dB itself is that horizontal component of CB, which was CBX, which was cosine of 24.6. So let's do that. Cosine of 24.6 is 0.909 times CB. That is going to be pointing in this direction, just because it has to be continuous with the compression force. So that's going to be the negative direction. So BD, we're going to assume points in this direction. So we're assuming BD is in tension. So the sum of our horizontals is going to be a negative 0.909 CB plus dB has to equal 0. Now we do know for CB, we just figured it out to be 2692. So let's substitute that in there. So negative 0.909 times 2692. Negative 2447 plus dB equals 0. And of course, just to solve for dB there, we're going to add the negative, we're going to add 2447 to get rid of the negative 2447. So that tells us that dB equals 2,447 pounds. And that was assumed in tension, and that turned out to be positive, so we are correct with that. So 2,447 pounds of tension. Okay, so now the question is, which joint do we go to next? Do we go to joint C or to joint D? Well, we have to look at, we can only solve if there are two unknown input forces. If we looked at joint C up there, we don't know this one or this web or this vertical. So there's three unknown inputs there. We can't solve for joint C yet. So we have to do joint D next. So joint D, we have the 2447 in tension, so it pulls away from the joint. That's coming from B. We have going off to, I'll label this E and F over here, so that's going off to E. I'm going to label that as in tension as well, just as a guess. We have 120 pounds coming down here. Then we have whatever is going to be coming off of that web to C. This one is also a fairly simple joint. Not going to give us any systems of equations yet on this one, because everything coming in is either horizontal or vertical. For the sum of my vertical forces, I have the negative 120 pounds, which is just my load, and I'm going to have to assume that CD there is in tension, just because it has to counter the 120 pounds. That has to be positive. There are no other vertical forces because nothing else has any sort of vertical component. Everything else is perfectly horizontal. So what that is telling me is that CD, just by solving this equation here, adding 120, that CD has to be 120 pounds in tension. So that part was pretty simple. For our horizontal forces, well, the only horizontal components we have BD here that is going negative in tension, so negative 2447. We're assuming that ED here is going in tension, so that's going in the positive direction there. Adds up to 0. Again, just simply solving our equation, adding the 2447. ED must also be 2,447 pounds of tension. So that joint's actually kind of boring. Any questions so far? Okay, joint C is where it gets interesting. Okay, so on joint C, we have the 440-pound load. This was 0 pounds coming from over joint A, so that does nothing. F, I'm just going to take a wild guess at F being in compression. I don't know what's going on there yet. Here coming from joint B, that was 2,692 pounds in compression, so that's going towards the joint. CD was in tension, 120 pounds. Then we have Webb here going over to E. And of course, our angle, as always, is the 24.6 degrees for this one. Okay. So the first thing we have to do is we have to break down our components here on BC. So this is going to be BCX. This is going to be BCY. BCY is going to be the 2692 times the sine of 24.6 degrees. So let's just do that right now. 2692 times the sine of 24.6. So 1121, I'll round it to. So that's BCY. BCX is going to be the 2692 times cosine of 24.6 degrees. which I round to 24.48, 24.48 pounds. Now over here for EC, I'll put the C in there so I don't have to stumble over it. We have ECX and ECY. So I'm going to do the same thing. ECY is going to be sine of 24.6 times EC. Sine of 24.6, I know I just did this, but 0.416 EC. And ECX is the cosine of 24.6 times EC. Cosine was 0.909, correct? Yep. So we've got ECY and ECX listed out. FC is going to be strictly horizontal, so we don't have to worry about that. So now let's look at the sum of our vertical forces. We have the negative 440 going down. We have a positive BCY, which is 1121. And we have negative 120 coming from here. Notice I'm going around this counterclockwise. It's a habit I got into. When I learned vectors, I learned something called Bow's notation. And in Bow's notation, you always go around the joint counterclockwise. So I had the negative 440, then just going down. I had the component from BC was the positive 1121. DC is the negative 120 because it's in tension. Next is going to be the component from EC. Now I assume that was in compression, so I have it pointing up. So that's going to be a positive ECY of 0.416 EC. And that's it, because FC has no vertical component. So let's simplify this and see what we get here. So let's see, negative 440. I'm going to cheat. $561 plus 0.416 EC equals 0. So now I can subtract the 561. Yeah, 0.416 EC equals a negative 561. So I'm going to divide that negative 561 by 0.416. And I get a negative 1349. So EC has a force of 1,349 pounds. The negative means I made the wrong assumption. I had assumed EC was in compression. It's actually in tension. So I now know that EC is 1,349 in tension. Now I can go back and do the same thing for my horizontal forces. Now that I know EC, I can find ECX here. It's just going to be 0.909 times 1349. $12.26. So now to do my sum of my horizontals. I'm just going to go around here again counterclockwise. There's no horizontal force there. This is a 0. So my first horizontal force is BCX, which is 2448 in the positive direction. As I keep going here, this is all vertical, so it can't be a horizontal component. ECX is going in the, now again, I said I was wrong, it's actually intention, but I have to stick with my original assumption to be consistent. So it's a, technically this should have been negative here, so this would be a negative 1226. So it's a negative 1226 going this way. So technically it's a, subtracting a negative is adding a positive. So that's 1,226 pounds. I'm going to pause there for a second. Everybody understand why that's a positive going in there? Because even though it's pointing this direction, it's a negative force because I had made the wrong assumption. So it's in the negative direction and it's a negative force. So minus a negative makes a positive, plus a positive. And then I have FC here, and I can tell you right now my assumption there is incorrect. So I'm going to actually change it since I haven't used that for any other calculations. That has to be in, oh, sorry, that was the correct assumption. That has to be going in the negative direction because everything else is positive. So I'm going to put in minus FC there. Equals 0. So that has to be in compression. So I can combine these here. 3674 minus FC equals 0. And I'm going to let you guys do the algebra to solve that to get that 3674 equals FC. I'll get there for now. Okay, so you can see here with the parallel cord, the flat top truss, it's a lot simpler because we don't have systems of equations that we encounter because we don't have angled top cords. Now, one thing I had said I would show you here, well, how to find those reactions. Since we only got 10 minutes left, let's do how do we find those reactions if it's not a symmetrically loaded truss. Now I'm just going to draw it as a flat line here and place the loads on it. So this is a horizontal projection of my loads. Let's say this is a 30-foot truss. Let's put this at 4 feet from the end. So this box is what we call a uniform or distributed load. We're going to call that 60 PLF. So that's 60 pounds per linear foot. And I'm going to put some what we call concentrated or point loads in here. I'm going to put one right here, 2 feet from the end. I'm going to call that one 200 pounds. And I'll put one over here, 6 feet from this end, and I'm going to call that one 400 pounds. So one of the first things you have to do is you have to get rid of that distributed load. You do it what's called an equivalent concentrated load. The equivalent concentrated load is equal to the total load at the center of the distributed load. That's uniformly distributed load, which sometimes called a rectangular load, which means we can go at the center. If it's a triangular load or non-uniform distributed load, then it's not going to be at the center. So that total load is 60 pounds per linear foot times how many feet? From here to here is 26 feet, right? $60 times 26 is 1,560 pounds. So I'm going to pause. Any questions on where the 1,560 pounds came from? Okay, so the location of that is going to be at the center of that distributed load, 1,560 pounds. That's now 13 feet from the end. So what this has become now is this picture here. I have it 6 feet, 400 pounds. I have it 13 feet, 1,560 pounds. Then I have over here, 2 feet from the end, 200 pounds. To solve this, I pick one end to be a center of rotation. So I'm going to pick this end right here to be a center of rotation. So I'm looking at here, I know that the sum of the vertical forces has to equal 0. And I know that the total, I have negative 400, I have negative 1,560, I have negative 200, and I have positive R1 and positive R2 adds up to 0, has to equal 0. So I know that R1 plus R2, if I did the math there, and I'll let you guys rearrange it, has to add up to, what is it, 2,160 pounds. But it's not evenly distributed, so it doesn't go half each direction. So I know that the total between R1 and R2 is 2,160, but I have to figure out how much goes to each side. And that's where this center of rotation comes in here. So what I'm going to look at is it's called the sum of the moments. Now I'm going to put M1. The 1 means I'm just going about reaction 1. Now, have you guys talked about a moment at all? A little bit? Okay. A moment is just a force times a distance. That distance is from a center of rotation. So I chose R1 to be my center of rotation, so all of my distances are going to come from R1. So I've got the 6 feet, the 13 feet, so I'm going to go to the 200-pound load here. That total distance was 30 feet. Minus 2 is 28 feet to that. So it's 30 feet all the way over to R2. So for each load here, I'm going to find its moment. So the 400-pound load, and what I'm going to do is I'm going to define a clockwise rotation to be negative, counterclockwise to be a positive. Doesn't matter which way you define them, just as long as you know you keep one direction positive, the other one negative. So the 400 pounds is going to cause this to spin clockwise. If I held it here and I pushed there, it would spin in this direction. That would be clockwise. So that is a positive 400 times 6 feet. The 1,560 pounds is also clockwise. So that's 1,560 times 13 feet. The 200 pounds is also clockwise. So that's 200 pounds times 28 feet. And R1 would be pushing the other direction. So that's a negative, or sorry, R2 I should say. R2 times 30 feet. And that has to add up to 0. So 0 equals 4 times 6 is, or 400 times 6 is 2400. 1560 times 13 is 20,280. 200 times 28 is 5,600 minus 30 R2. So I have to combine all these. So 28,280. So 0 equals 28,280 minus 30 R2. So again, 28,280 equals 30 R2. Divide by 30. R2 is 942.67, 942 and 2/3. Now, of course, to find R1, I just use the sum of my vertical forces. Those two have to add up to 2160. So I'm just going to subtract my 942 and 2/3 from the 2160. So 1217 and 1/3. Does that make sense? Okay. On Wednesday, I'll actually start out, I'll do a little bit more with these reactions. And then we'll look at a sloped top chord truss again. So we'll get back to doing the systems of equations again. And what we'll do is Wednesday we'll leave it up to you guys as to how much more you need. We're kind of playing it by ear as to what you guys think you need. On Wednesday, I'll remind me to ask you before we're done as to whether you guys want a session on Friday or if you want to wait till Monday or wait till Wednesday or how much you guys want, okay? Is there anybody that's opposed to having a session on Wednesday at this point? You don't know if you'll make it? Okay. So there'll only be like 2 or 3 of you here on Wednesday? I will pass that along and make sure, I'll make sure that Deb or somebody lets you know if they decide to cancel it on Wednesday, but I think we're probably good to go to have one on Wednesday so far. Okay, well, we'll see you guys on Wednesday.